Previously, we solved the problem of under what conditions growth rate and predation rate balance in an aphid population. And we arrived at 3 possible solutions, x equals 0, and 2 others that essentially were intersections of these 2 curves. Now we're in position to ask another question, which is, what happens when these do not balance? We can now consider the fact that the aphid population will change, and it will change due to its own growth minus removal due to predation. Therefore, the rate of change of the aphid population is actually the difference of these 2 quantities. This is a differential equation, and now we have tools to understand how these equations can be solved graphically. Let's look at this picture in which we've actually plotted again the predation rate, the pink curve, as well as the growth rate of the aphids. Let's see what happens from any starting aphid population. For instance, if the aphid density is this large, then we observe that the predation rate, this point on the curve, is greater than the growth rate. In other words, predation will dominate and the population of aphids should decrease. This is true throughout this whole interval, wherever the pink curve is higher than the blue curve. Let's indicate that by putting a minus sign over here. If we're precisely at one of these points, then we do not move. We're at a steady state because these 2 processes balance precisely, and then dx by dt is 0. This is also true at the origin. Now, what happens if we have a large aphid population? Suppose initially we had a point over here. In that case, the growth rate is higher than the predation rate, and so overall the net population change will be positive. The aphids will be increasing in density. Finally, if we look at this interval, again with some starting position over here, the growth rate exceeds the predation. The blue curve is above the pink one. We'll indicate that with a plus sign. Based on what we've shown here, then we understand that the aphids will increase throughout this range, and we can draw that by arrows pointing towards higher x values to the right. That's true also in this region, whereas throughout this interval, the opposite is true. The aphid population decreases, and so we have motion like this. Now, already from this picture, we see that this steady state is stable in the sense that nearby initial conditions get closer and converge to it, whereas this steady state is unstable because nearby initial conditions diverge or get farther away. So we recognize that in our previous work, the balance points are precisely steady states. There's one steady state that's stable, and initial aphid densities approach it. On the other hand, if the aphid density should exceed a certain threshold, then that population of aphids will increase regardless of ladybug predation and will no longer be controlled. In fact, we can draw a sketch of the aphid population as a function of time based on what we've shown here, indicating 0 as well as these other 2 roots. Both of these are steady states, but only one of them is stable. As we've seen here, we expect that initial conditions in this range will converge to the stable steady state, whereas initial conditions over here will diverge.